Very good morning, students. Welcome to another lecture on control systems engineering. This is lecture 3, and in today's class we are going to learn about mechanical rotational system, symbols that are used in mechanical rotational systems, and some problems on mechanical rotational system. So in previously we have discussed about mechanical translation system, where in that mechanical translation system we have input as force and output as displacement. Here in mechanical rotational system we are giving input as torque and the output will be angular displacement. So mechanical rotational system can be obtained by using the three basic elements, that is ideal rotational mass, it can be represented as J, ideal dashpot, which can be represented with B, and ideal spring, which can be represented as K. I repeat, ideal rotational mass, that is J1 or J, ideal dashpot, that is K, and ideal spring, that is ideal dashpot is B, and ideal spring is K. So what are the symbols that we are going to use in mechanical system, rotational system are theta, which is angular displacement, and d theta by dt, angular velocity, d square theta by dt square, angular acceleration, t is the applied torque, and j is the moment of inertia, b is the rotational frictional coefficient, K is the stiffness of the spring, and ideal rotational mass. Let us assume that we are giving an input as T, which is the applied torque, and Tj is the opposing torque due to the inertia of the body. Therefore, Tj is directly proportional to d square theta by dt square, which can be written as Tj is equals to J into d square theta by dt square. Therefore, by Newton's second law, T is equals to Tj is equals to J into d square theta by dt square. Coming to the next one, that is ideal dashpot. Let us assume that T is the applied torque and Tb is the opposing torque due to friction. Therefore, opposing torque due to friction is directly proportional to d theta by dt, and it can also written as Tb equals to B into d theta by dt. Therefore, by Newton's second law, T is equals to Tb equals to B into d theta by dt. If there are one or more angular displacements in the given system, then Tb is directly proportional to d by dt of theta 1 minus theta 2, which can be represented as Tb equals to B into d theta by d by dt of theta 1 minus theta 2, and by Newton's second law, T is equals to Tb equals to B into d by dt of theta 1 minus theta 2. Coming to the ideal spring, so let the applied torque will be T, and Tk is the opposing torque due to the elasticity, and Tk is directly proportional to the angular displacement. It can also be written as Tk is equals to K into theta. When one or more angular displacements are there, then Tk is directly proportional to theta 1 minus theta 2, which can be represented as T is equals to Tk is equals to K into theta 1 minus theta 2. Let us go for a problem. Write the differential equations governing the mechanical rotational system shown in the figure and obtain the transfer function of the system. See here, we have two mechanical elements, that is J1 and J2, and the applied torque is T and theta is our output. So, in the given system, the applied torque is T and the input torque T is the input and angular displacement theta is the output. So let the Laplace transform of T is equals to L of T is equals to T of S. and the Laplace transform of theta is equals to L of theta is equals to theta of S. Hence the required function is, that means the required transfer function is theta of S by theta of T of S, that is output to the input ratio. So let the angular displacement of the mass with moment of inertia J1 be theta 1, and the Laplace transform of theta, as we have all seen, that theta 1 is equals to L of theta 1 is equals to theta 1 of S. And the opposing torques acting on J1 can be marked as Tj1 and Tk. Therefore the free body diagram for J1 can be written as J1 is equals to applied torque T and angular displacement is theta 1, and the opposing forces are Tj1 and Tk. Therefore by Newton's second law, what we are going to know, applied torque is equals to, by Newton's second law, applied torque is equals to sum of opposing forces, that is the Tk and Tj1. So it can be written as Tj1 can be written as J1 into d square theta 1 by dt square, and Tk can be written as k into theta 1 minus theta. So J1 d square theta 1 by dt square plus k into theta 1 minus k into theta equals to t. And on taking Laplace transform with zero initial conditions, J1 d square theta 1 by dt square can be written as s square into theta 1 of s plus k into theta 1 of s minus k into theta of s is equals to t of s. By taking theta 1 as common, J1 s square plus k into theta 1 of s is equals to k into theta of s, which will be equals to t of s. So let it be the equation 1. Let it be equation 1. So coming to the next one, the free body diagram for M2 can be written as J2 is equals for J2 can be written as angular displacement, and the opposing bodies are Tj2, Tb and Tk. So then opposing torques acting on J2 are Tj2, Tb and Tk. Therefore Tj2 can be written as J2 into d square theta by dt square, Tb can be written as b into d theta by dt, and Tk can be written as k into theta minus theta 1. And by Newton's second law, the applied force is, here we have not applied any force, therefore the applied force is equals to 0. 0 is equals to Tj2 plus Tb plus Tk. So Tj2 can be written as J2 into d square theta by dt square plus b into d theta by dt plus k into theta 1 minus theta 1 is equals to 0. So J2 d square theta by dt square plus b into d theta by dt plus k into theta minus k into theta 1 is equals to 0. And by taking Laplace transform on both sides with zero initial conditions, J2 s square of theta s plus bs of b into s into theta of s plus k into theta of s minus k into theta 1 of s. And by taking theta of s as common, J2 s square plus bs plus k minus k into theta 1 of s is equals to 0. And here we are substituting theta 1 of s value here in the previous as from equation 1. Theta 1 of s can be written as j. So by taking theta 1 of s, sorry, not from the equation 1, we are going to substitute theta of s here. So theta 1 of s is equals to J2s square plus bs plus k by k into theta of s. Okay, so theta of s can be written as J1 s square plus k into J2s square plus bs plus k by k into theta of s minus k into theta of s is equals to t of s. So J1 s square plus k into J2 s square plus bs plus k minus theta, we have taken theta as common, right? Therefore k into k square by k into theta of s is equals to t of s. As we required the transfer function theta of s by t of s, it can be written as theta of s by t of s is equals to k by j1 s square plus k into j2s square plus bs plus k minus k square. Therefore the required transfer function is t is equals to theta of s by t of s, which will be equals to k into k by j1s square k into j2s square k j2s square plus bs plus k minus k square. Hence the required differential equations are j1 d square theta 1 by dt square plus k theta 1 minus k theta equals to t, and j2 d square theta by dt square plus b into d theta by dt plus k theta minus k theta 1 is equals to 0. These two are the required differential equation, and the required transfer function is t is equals to theta of s by t of s is equals to k by j1 s square k plus into j2 s square plus bs plus k minus k square. So that's all for today. We'll meet in the next lecture. Thank you.